Hello guys, welcome to Bugs in Code, and the problem that we are going to solve today is invert binary tree. But before that, if you're new here and a person who likes stuff related to coding, then you can subscribe the channel Bugs in Code so that you never miss out an update. So let's get started. The problem statement is given the root of a binary tree, invert the tree and return its root. So it's quite simple, but let me tell you what exactly a binary tree is, an inverted binary tree is. So okay, let's take this tree. Okay, so actually let me take a smaller tree first. Like if we have a tree like 1 and 2 and 3, so what we can do is we can swap these two children's, and after this operation what we get is an inverted binary tree. So after this we get 1 and 3 and 2. So this is something that we call an inverted binary tree. Let me take a greater example. So this first and this 2. So let me take a greater binary tree that is 4, and let me take this one exactly 2 7 and 1 3 6 9. Okay, 2 7. After that we have 1 3 6 9. So what we can do is each time we come to a node, so we are going to swap the childrens of that node. Okay, so let's do it here, and after operation we will get 4 7 2 3 1 9 and 6. Okay, so what now we can do is this is going to be our solution. Now I hope you got the clear understanding of the problem statement, and let me move to the solution. So here I am going to write solution. Okay, so let me draw the tree again. The tree is 4 2 7 1 3, and let's take 6 and 9. Okay, so what we can do is, I want you to focus here. So what we can do is, if we got the answer for any node, like if I got the solution for this particular left child and this particular right child, then we can just swap these two nodes and we got a solution. Like for this left child, a solution will be 2 and 3 and 1, and for this 7 we will have solution like 9 and 6. Now what we are going to do is, this is connected to 4, and now what we are going to do is we have a solution for this left, this right and this left. We are just going to swap these two children. So after doing this we will surely get our answer, and that will be 4 7 2 and 3 1 and 9 and 6. So this is the solution, and I look into this problem as a DFS problem. Each time what we are doing is we are getting the answer from left children by, if we have a function like solve, then we are calling solve for left children of the node and similarly for right children of the node. After that, when we get the solution of left and right, we are just going to swap these two nodes, and obviously we are going to have a root as an argument of which the left and right are children's. So let me just swap the node, and how we do swap, we will have a temp variable that will first store left, then we are going to do root dot left. Actually root dot left is equal to right, so right is this thing, and root dot right is equal to temp. So this is what we are going to do. After that we have our problem solved for the root, and that's why we are going to return our root. So this is about the DFS approach, the depth first search, DFS. So it is a recursion based approach, and let me just now code this approach. I hope you understood what I'm trying to say. Now I'm just going to code this approach. So this is the problem on Leetcode. I'm even going to provide the link in the description box. What we can do is now, what we can do is, if our root is equal to null, then we are going to return null. After that, we need to get answer for left and right, and similarly for right will be okay. Now we need to swap the current children's, so we are going to store left somewhere. After that, true dot left will become right, and true dot right will become 10. I hope you understood the problem clearly, and this is the approach. Let me just run this. Okay, so it's working for sample test case, and let me just submit the solution, and it should work, I think. Okay, so it's working, and you can see, let's see how faster it is. So it is 100% faster. Now this solution is all correct, but the problem with this solution is it is using extra recursion stack space. So let me write here, it is using recursion stack space, and I don't want my problem to rely on something that is stack space, because the stack space, the recursion stack space is something that may overflow for larger problems. So I don't want to rely my solution into the recursion stack. So let me just explain you another approach that is not using any recursion stack space. So let me just delete this. After that, I'm also going to erase this and this as well. Okay, so now let's see what we have as another way of solving this problem. So what we can do is we can store, actually stack is something that we generally miss when we try to solve our problem without using recursion stack. So we can create our own stack that is going to be stack, and we are going to add the current root into this stack. Okay, so after that, while our stack is not empty, we are going to retrieve the current node from the stack, that is going to be node as stack dot pop, like what's in the stack. After that, I'm going to, first of all, I'm going to ask what's in the stack, and after that I'm going to retrieve the left and right children. So left is equal to left of stack. After that, right will be equal to the right of stack, the right of, I mean, current node actually. Okay, so now what we need is we just need to swap these two, isn't it? So now we just need to swap these two, and I'm going to swap here. So I will have a node temp which will be equal to left, and the left of root will be now equal to right, and the right of root will now be equal to temp. So this is something that we're going to do. After that, we are going to check whether my stack has okay, so now I think I'm done with the root. So now my solution will look something like 4. I'm also going to represent how our tree will change when we do this. So 7 and 2. After that, it will remain same 3. But this is something that we cannot say it's our solution, because this is something this subtree is something that is not solved yet. So after that, what I'm going to do is I'm going to check if my left is not equal to null. So I need to add left to the stack so that it also get processed. So we are going to add in the stack. So stack dot add left, and if right is not equal to null, then I'm going to do stack dot add So if you see this, so what we are doing is we are adding 4, after that we are adding 7 and 2, after that what we are doing is we are going to these children and we are also adding these. So it's something that we are doing level order traversal. So it's not something that you say ki, hey, we don't do level order traversal with stack, always use queue, but it's not like that. Level order traversal is simply a traversal that is traversing all the nodes level by level. But the only difference between queue and stack is stack is storing like 7 and 2. So 2 will get processed for right child, but our queue is storing like 2 is storing like 2 and 7. So I mean 7 and 2. So here 7 will get processed first. So we can even solve this problem using the queue. So instead of stack, what we can do is we can use a queue data structure and the problem will run similar to the stack problem. So let me just code this approach and I'm going to use both stack and queue. Let me just come here and solve this problem. I hope you understood what I'm trying to say with the BFS approach. So let me just implement a queue data structure first, which is going to be of type tree node, and it is going to have a linked list implementation. After that, what we can do is while my queue is not empty, okay, so it's actually wrong here. After that, each time I need to get what's in the queue. So I will have a node in the queue and I'm just going to have the left and right children. So let me just without getting and let me just swap. So and after that left is going to be equal to right, and this all, and now I need to add the children's in the queue. So if my left is not equal to null, then I'm going to add to queue. Similarly, I'm going to add the right child as well. And now I think we are done. We just need to return root. So, and we are missing one thing. We are not adding a root to the queue. So first of all, we need to add root to the queue so that our queue is not empty in the first iteration. Let me just run this. I think it should work and it's showing null pointer acceptance. So okay, one thing that I'm missing is, let's see, okay, so if my root is equal to null, then I'm just going to return nothing but null. Let me now run this approach. I think it should work, and okay, it's working for sample test cases. And okay, so it's running and it's also 100% faster. And let me just now tell you how we are going to implement this using stack, because stack is something that helps us to get the intuition behind this level order traversal. So that's why I explained you the problem with stack first, so that you get to know about the intuition. And we are going to create an stack and new stack also. Okay, so I'm going to change stack here, and after that, see, stack doesn't have any function that is pull. Instead we will write pop, and after that we are going to add this into stack. Even stack also have a function that is push. So I think okay, while my stack is not empty, I'm going to perform the operation. I think it should work now, and Okay, so it's working for stack as well, and let me just quickly submit this. Okay, so it's also got submitted. And so this is all the about the both DFS and BFS approach, and this all about the problem. I hope you understood how we are going to solve this problem with the intuition behind the solution. So this is all about this video, and I hope you like the video. If you like the video, you can subscribe the channel and also hit the like button. So that's all. Thank you.